Standard alignment fine-tuning trains models to refuse dangerous requests, but sophisticated users can force their way past these restrictions using highly engineered text prompts. These are known as universal jailbreaks. They are reliable, targeted prompting strategies designed to systematically bypass a model's helpful, honest, and harmless, or HHH, fine-tuning. The primary risk here is capability uplift. Malicious actors use these jailbreaks to extract highly detailed instructions for manufacturing chemical, biological, radiological, and nuclear weapons. Relying on a single language model to both generate intelligent text and police its own outputs creates an inherent architectural vulnerability. The cognitive pathways used to answer a question are the same ones tasked with censoring it. Attackers exploit this exact overlap. Securing an AI system against systemic attacks requires physically decoupling the safety mechanism from the core generative model. The defense must operate in distinct, specialized layers. Anthropic addresses this vulnerability through a dual-layer architecture known as the Constitutional Classifier. This flowchart illustrates the first layer, an independent input classifier that screens the user's prompt before the core model sees it. The second layer is the output classifier, monitoring generated text in real time. If harmful content is detected at either stage, the response is blocked. This creates a Swiss cheese defense model. If a highly obfuscated prompt manages to slip past the input classifier, the resulting dangerous knowledge is still caught by the output classifier before it reaches the user. Training these two classifiers introduces a severe engineering bottleneck. Human red teamers simply cannot generate labeled training data fast enough to keep up with rapidly evolving adversarial threat models. This section of the diagram outlines Anthropic's solution, deploying a separate, helpful-only language model to automatically generate vast quantities of synthetic training data. To guide this generation, engineers write a harmful constitution. This is a strict set of written rules defining precisely which dangerous topics, like Schedule 1 chemical synthesis or weaponization logistics, the AI must generate examples of. But feeding a classifier exclusive examples of harmful data destroys its utility. A model trained only on attacks loses the context of normal human interaction. This requires the implementation of a harmless constitution. The system must explicitly define safe, related topics that the model must also generate to learn contrast. For example, alongside rules blocking nerve agents, the harmless constitution mandates the generation of text explaining high school chemistry experiments, standard water purification, and properties of common cleaning products. Processing massive volumes of both extremes allows the algorithm to mathematically calibrate the precise boundary line separating legitimate scientific inquiry from dangerous weaponry instructions. Without explicitly defining what is safe in the training data, a safety classifier will paralyze the core model in production by flagging completely benign scientific queries as false positives. With the data generated, we look at the specific mathematical engineering required to build the first wall, the input classifier. The primary challenge here is evaluating a user prompt accurately without losing the deep linguistic nuance inherent in the pre-trained model. If the classifier is too rigid, it misses context. This bar chart compares two options for the input classifier. Anthropic chose a next token prediction task over a new value head. Next token prediction vastly outperforms because it directly leverages the model's existing pre-trained language weights rather than starting fresh. This setup utilizes in-context task specification. By evaluating the prompt as a natural language generation problem, the classifier easily identifies direct attacks and complex obfuscation ciphers. Reusing the model's native language prediction capabilities creates a computationally efficient first line of defense that accurately processes the specific context of a threat. The input classifier has a known blind spot: highly complex, multi-turn, many-shot jailbreaks, where an attacker feeds the model dozens of fake examples, can eventually confuse it. This creates the absolute necessity for the output classifier. The system must monitor the AI's actual generated response to catch these anomalies. But here lies a severe engineering tension. If the system waits for an entire response to generate before classifying it, it introduces massive, unacceptable latency for the user. To solve this, the output classifier must mathematically evaluate the text token by token, exactly as it streams to the user. Looking at the right side of this chart, we see that to achieve this streaming, engineers must abandon next token prediction and introduce a dedicated value head. This graphic demonstrates how the value head works in practice. It predicts the probability of full sequence harm based only on a partial prefix of generated tokens, updating its mathematical score word by word. This creates a mathematical dilemma during training. Using direct value head probability offers highly stable training gradients, but in the real world, if the stream is halted halfway, the rest of the text is blocked permanently. Direct probability doesn't reflect this finality. Alternatively, using a cumulative maximum probability perfectly matches the reality of real-world stream halting. But because gradients only flow through the maximum scoring token position, it creates highly unstable gradient flows during training. Anthropic's solution is a customized, linearly interpolated loss function. This function starts the training process using direct probability, ensuring stability and good gradient flow. Then, as the training run progresses, it gradually shifts the weighting parameter over to cumulative maximum. This loss function allows the system to balance training stability with the practical requirement of real-time, token-by-token interception. With the mathematical theory implemented, the architecture required empirical validation. It had to be tested against human adversaries. Anthropic launched a massive bug bounty program. It yielded 113 submitted reports from participants, logging over 3,000 estimated hours of aggressive hacking effort. The attackers were given 10 target queries and a singular goal: extract a universal jailbreak that reliably delivers highly detailed capabilities for chemical, biological, radiological, and nuclear weapons. The results showed a significant increase in defense robustness. No single report successfully answered all 10 questions at the level of detail provided by a model without safeguards. Standard models routinely fall to established jailbreak strategies. In this program, however, the defense held against common automated techniques, forcing attackers to resort to less efficient methods like benign paraphrasing and length exploitation. By requiring an attacker to defeat 2 isolated classifiers simultaneously, the system significantly reduces the risk that a malicious actor could reliably extract the technical detail needed to execute a complex scientific process. The final engineering hurdle is proving this extreme robustness doesn't ruin production viability or consume excessive compute power. This chart visualizes the system's performance on a held-out dataset of novel jailbreaks. The guarded system blocked 95% of attacks, compared to an unguarded model's baseline block rate of just 14%. The impact on user experience remains minimal. Thanks to the precise calibration from the harmless constitution, Anthropic observed only a 0.38% increase in false positive refusals on real-world traffic. And the computational cost to run these dual layers sits at a highly manageable 23.7% inference overhead, fully preserving commercial viability. Robust AI safety does not require lobotomizing the core generative model. Deploying small, modular classifiers trained on synthetic constitutions provides a scalable, real-time defense against advanced AI threats.